And so one of the things through all of my career has been an important part, has been screening new technology, and certainly the process engineer's role in this is essential in my view. And I believe certainly as chemical engineers, the important gift that we have in terms of thinking about systems is extremely important. One of the challenges in looking at new technology or a concept is to know when to declare defeat in an experimental course of action or development. The human tendency, of course, is to hope for the best and try to avoid failure at all costs. And as a result, and I've experienced, and I'm sure some of you have as well, failing R&D projects are often kept going much longer than technically rational or economically prudent. And the process engineer has an important role in informing these decisions and in informing technology development priorities. So I want to I will make a few comments on this painting by Picasso. I thought it might be useful to have a couple of kind of historic examples for us to reflect on because I think they relate to today. And then I want to have some discussion about process boundaries, which I think are extremely important. And then we'll spend some time on techno-economic analysis. And I guess it's not as easy to have maybe kind of real-time dialogue in this format, but certainly if there are comments or questions and it's easy to lift those up, I'm very open to that. So if we look at this Picasso painting, I really see this painting, which he did in 1921, relates to our time, to the challenges of carrying out technology development and to analyze the technologies, to do this technical and economic analysis. People living in the early 1900s, they experienced changing transportation system. Electric power was emerging. Rutherford split the atom in 1917, and Picasso was an artist during this time. And his art was an expression of how he experienced the world, is how I view this. So if we look at this composition, it's fragmented, but suggests an interplay of the fragments. We have faces, we have instruments, we have music, we have the table. And today, I think few people see an integrated energy system, fuel to electricity, to transmission, to a home outlet, for example. I think his art also has no fixed viewpoint. There are multiple perspectives that we can see in this painting. The wind turbine supplier has a particular point of view. The farmer who invested in an ethanol plant has a particular point of view. The scientist may be focused on new PV materials. So I think this differing points of view is an important dimension to what we're dealing with in terms of the challenges today. I think in his paintings, the subjects also seem to be sealed off from recognizable reality. If you look carefully, and unfortunately I should have adjusted this figure a little bit, but the dog can be seen to the left of the musicians. And in general, I think the public finds it difficult to really connect with many parts of the climate or energy challenge. And so our technologies are really integrated into systems, and they have connections to multiple challenges. And so where we draw the boundaries in our work is extremely important. So if we go to the next slide, Michelle, let me see here. Why do I have a message here? The meeting. Oh, okay, got it. Not a problem. So just some perspective on the process engineer. I think this is not new for any of us. Certainly characteristics I've listed there on the left-hand side, monitoring processes, developing new processes, assessing process, performance, cost, reliability, ensuring compliance, assessing risk, assuring safety. All these are part of the characteristics of the process engineer. And the applications I've listed on the right. Many of us have certainly engaged in being at a plant or an existing plant operation, but there's then also new technology for an existing plant or a whole new plant. And I want to focus here on new technology if we're looking at a new market, and kind of give some thought to that space for the process engineer. And then the next visual. Can we go to the, thanks, Michelle. So kind of some comments on the evolution of process boundaries. So on the left axis there, I have the scale, all the way from molecular, all the way to looking at global systems, and a function of time. So back in 1900, AIChE was formed in 1908. And if you look at the presentations at that initial meeting, basically focused on equipment, what we now call unit operations as well. And that was the focus and the scope that we had at that time. During the 1950s, the focus was really on the plant. And I've put on the right hand there, in my undergraduate days, we used Max Peters' Plant Design and Performance for Chemical Engineers. This was a book in 1958. And the inside figure, when you opened that book, was this plant. And the whole book was focused on thinking about technical and economic analysis, but it was really focused on the plant. And then since that time, we've really expanded the scope of where we draw process boundaries in terms of the work that many of us are engaged with now and think about, so that we're really now at the micro level, molecular level, all the way up to looking at enterprise systems, large, complicated systems. So if we go to the next visual, I had a couple examples here that I thought were, and there's a number that we could pick. This happens to be on ice manufacturing. And I see this as an example of where we're responding to technology. So this is the ice production by time from like the 1870 timeframe up to 1940, which is all we need to deal with really here. And so in, even in 1915, between 1900 and 1920 in this figure, there were like about 25 million tons of natural ice that was still harvested, which was the primary view before that. And there was about the same amount of ice that was produced by what we'll call plant ice that was manufactured. And but there were a lot of considerations with weather, ice famines, concerns with polluted lakes. Ice from the Hudson River was really unsafe. The Natural Ice Association of America was formed during this time. and really to promote the benefits of natural ice. And you can go back and look at the literature, and you think about the changes that we're currently undergoing, and we have the same kind of transitions that occur. But the market really collapsed after World War I, and that was really driven by cheap electric motors, which led to refrigerators. And so we had the first refrigerator in widespread use in 1927. And then hence after that, a significant decrease in the production and use of ice. At the right picture there is the Heinz History Center in Pittsburgh. And this was formerly the Chautauqua Lake Ice House. So ice was originally, one of the sources was the Chautauqua Lake. Ice was transmitted to Pittsburgh, and a lot of the infrastructure in this building still relates to that time. But I think this is an example, of which there are many others, where technology really responded to challenges and issues. And yet there was a significant group of folk who were interested in seeing natural ice continue forever. If we go to the next visual, this is a case of refrigeration efficiency. And this is a case where we're responding to regulations. And what you see here, I have three lines on this chart. The time frame is 1950 to 2000 roughly. And the green line is the refrigerator price. The blue line is the energy use per unit, of cooling, if you will. And the red line is the refrigerator size in cubic feet. And what we see is in the early 1970s, we had regulations that really were focused on driving improved refrigerator efficiency. And so as a result of that, we see the significant reduction with time of energy use per unit. And we also see that the price went down. And I think one of the considerations that we encounter today is people who resist many of the regulations invoke, well, we don't want to do that because of environmental or other concerns, because it's going to increase the price. Well, that's not necessarily needs to be the situation, as we can see. And yet the size of refrigerators continued to increase, and certainly didn't decrease as a result of this. So I think it's another example of where it's useful for us to think about the role of technology, and in one sense, its connection to society, to communities, which we'll talk about a little bit later here. The next visual then just illustrates what I see as one of the real challenges that we have, and that's the food challenge and responding to new paradigms. We have an enormous amount of wasted food, and what we call the food cold chain, if you will, pre-cooling, cold storage, refrigerated trucks, chilled market shelves, etc. We really need to reinvent this, and it's going to require more than just refrigeration in this case. So it's another example, and we have many of these types of examples that we're dealing with today. So these are just a couple of historical perspectives before we go into the other areas on the next slide. So changed process boundaries. As I mentioned, originally we were in this blue box where we were largely, as chemical engineers, focused on process and product. We designed a plant, we built it, we operated it, a manufacturing process. But today we're really needing to deal with the whole integrated system: resources, the process, environmental, sustainability, societal, safety, infrastructure. And so the boundaries have changed over these 50, 60 years, if you will. The next visual then are looking at the components of this integrated system analysis. Certainly there's the technology, which is traditionally a focus that we've had. Resources have also been a focus for many of us. Materials, the supply chain, the workforce, the organization associated with those resources, the externalities, and the end user in the market. And if we go to the next visual, I want to then spend some time on techno-economic analysis, where we are really interested in looking at performance, capital cost, operating and maintenance cost, uncertainties, risks, and the time frame is important. And all of this is so important in terms of informing research and development and informing investments in technology. So the next visual, I just thought it was useful to briefly comment on the literature of techno-economic analysis, which has become a very common kind of nomenclature today and is used throughout. And it's, in my view, used very, people treat it as one, but there are just so many dimensions to doing techno-economic analysis, which we'll comment on. But this is a plot of the literature that uses the terminology techno-economic analysis. And while there was very, very little reference to this up until the 2000, and then in the recent years, there's just been a significant increase in the publications relating to this. Over 90% of the 9,000 refereed publications are in the last 10 years, for example. And yet, as chemical engineers, we were doing techno-economic analysis back there in 1960 when this curve was, it was just, we used different tools. We didn't have the Aspen or other tools that were typically used in terms of carrying this out. But I just thought this was some interesting perspective. Next visual. So technology maturity is extremely important. And many of you are engaged, I'm sure, with this whole space, and I welcome our exchanges on this. So there's technology readiness level, which is used, and many of you are very familiar with this ranking, if you will, all the way from a concept, TRL1, up to where a technology is commercial. But frequently, the system integration level, readiness level, and the interconnected readiness levels are not really addressed effectively. And I consider these to be extremely important when we're looking at new systems. And even if we're looking at a new component, many times the integration of that component into an existing plant or a new plant is not seriously considered. So there are techno-economic analyses for new components, for new plant concepts, and for a whole new application system, if you will. So if we go to the next slide, what I've done here is these are some kind of the status, the understanding that we would have with the status of a technology. And they're sort of listed in the order of from a concept level all the way to where we're interested in more of the commercial product, if you will. So, you know, do we have test results? Do we have data analysis of an existing, do they exist for this new technology? And all of these are the things that are important in carrying out a techno-economic analysis. Does an integrated process flow diagram exist? Frequently, we're presented with a cartoon of a simple box that assumes a great deal of assumptions in it, if you will. But eventually, we as process engineers, if you will, are really engaged in putting together a process flow diagram. Does a process equipment and system configuration exist? One can have a flow diagram, but one really needs some configuration information. Are the interface requirements for a novel process defined? Do the novel equipment design concepts exist? Frequently, we have black boxes, but are very limited in terms of a design concept, if you will. Are the materials of construction identified? Has someone done material and energy balances? Have integrated process performance and cost targets been estimated? And have practical engineering design and cost issues been identified? And certainly operability, competitiveness with alternatives are crucial. So these are kind of and there's many other dimensions here, but it illustrates the hierarchy of information which one wants. And one can do a techno-economic analysis with any of this level of information, but they are a very different techno-economic analysis. And what we see, and DOE has done this as well, we see guidelines for techno-economic analysis, but the guidelines are frequently for a quite mature technology where it's assumed that you have some test results, you have a process flow diagram, you have some equipment design, you have an application, but frequently we're dealing with a need to carry out this techno-economic analysis work to screen technologies at an early stage so that we can make these decisions about should we continue investing in this or not. The next visual. So this is just some comments on relevant boundaries. One can look at just a system component, a gas turbine, an automobile, EV vehicle, for example, or a building. One can look at a collection of these energy system components. For example, natural gas being fed to a natural gas combined cycle plant with carbon capture, producing electricity, as an example. Or we can look at a natural gas producing hydrogen fuel, and it goes to a charging station for an EV vehicle, for example. Energy system components and the supply chain to produce the components is another whole dimension. And again, do we look at the fate of those materials even after the later on? And these, of course, dimensions are extremely important in life cycle analysis. If we're looking at the total life cycle from cradle to grave, if you will, we really have to be looking at a larger integrated system and to do that. And then the system enterprise frequently needs to be addressed where we're connecting energy systems. If we look at the electric grid today, tomorrow's electric grid is going to be radically different. And it's going to be a collection of very different energy systems. And so we really need to be thinking about how we model, how we think about these, excuse me, sorry, you know, the overall enterprise, if you will. The next visual. So technology development clarity. Extremely important. Is the market application defined? Do we know the customers, the regulations, the scale, the environment? What is the boundary for the technology to be evaluated? It may just be a component, and it may be that there's very few interfaces. On the other hand, we may be looking at a very complicated integrated system. And is there a reference today plant or a component design performance is extremely important. Candidate metrics, there's a whole list of metrics that are considered. I just list some of these here that we frequently are engaged in considering regularly. Certainly the state of the technology, the performance or cost improvements that can be achieved, the system integration, the complexity. There's a number of technologies that are proposed. Technically, they can be made to work, but the complexity of the system makes the reliability and the feasibility of a commercial system being lifting up the question, do you want to take that risk? The projected competition, what are we competing against? And then the technology development timescale. I just share an example, a personal example there. In Westinghouse, we were very focused on developing different alternative fuel systems for gas turbines. And this was back in the 1970s when, as many of you may be aware, remember, there was big challenges. Certainly oil was in the 40s and 50s was used for gas turbines, then natural gas, and then there was the natural gas was no longer seen to be readily available. So we were looking at alternatives like gasification for syn fuels, for different alternative fuels for the gas turbine. And we would carry out these analyses and designs of these plants and systems, and we would want to then be comparing with the competition. But we learned this after a reasonably short period of time, but it took a while for us to learn. We were always comparing with what was then today's technology. But the gas turbine technology was continuing to advance at a very substantial rate in terms of its efficiency, lower cost. And so it became very clear after a period of time that we really needed to be looking at the competition and what the projection of that technology would be. And so the technology development timescale was extremely important. And that just a kind of one of many kind of personal examples of how we get sometimes can get locked into the wrong comparison that we're making. And investment risk is also important. So if we go to the next visual, this is the, I think this is my last slide. And so I just highlight the process engineer's role, in my view, is essential if we're screening a new technology. And I'm talking here about a technology that may be in the range of a technology readiness level of 1 to 5, where we have a concept, or in the 3 to 5 range, we've done some experiments, we have some data and analysis. And so the objective is really to identify the new process performance and cost. And we're really trying to identify at this stage, what are the issues? Where are the real challenges? Where do we need to focus the effort going forward to address? And this then informs the R&D priorities and informs what kind of investment one needs to project. And that then leads to, okay, is it worth that investment? Because different problems, to solve those problems, require different levels of investment and different experimental work or analysis work. So we can utilize techno-economic analysis and use our current technology understanding to really address these issues and this need. It's important to know the level of detail and analysis, the boundary consistent with the need. There are so many situations where we'll talk with someone in the research lab who are doing experiments, but the experiments are at conditions that would not relate to the application that they view that they want to be apply this technology for. So in those situations, we're able to essentially inform that research work so that we're now carrying out experiments at conditions that are relevant for the application. And a caution is that developers have incentives to project results that satisfy market objectives. And I think we've all seen this. I have the opportunity of reviewing many proposals in response to funding opportunity announcements that DOE puts out. And it's very typical that whatever technology may be being proposed, it magically achieves whatever the objective is. And yet the analysis to support that assertion is not present. And I think this is one of the kind of considerations that's extremely important. We as chemical engineers have the ability to essentially assess those kind of choices and decisions, and to relate a new technology that we may be interested in to a market objective and what the needs are to achieve the target and what the gaps are in doing that. So at the bottom there, I just note that if we're looking at a technology readiness level that may be at the 1 or 3 level, these are typically concepts where you may have some information. It's so important that we have clear assumptions and we understand those assumptions, that they're not just random assumptions to produce an answer that we want. And then if we're at the development scale, it's really important to have some equipment size estimates and some cost estimates that we would relate to that we can now put into this overall techno-economic analysis to really assess where are the gaps, where are the needs, what are the experiments that we really need to be carrying out, or the analysis that we need to be carrying out. So let me close with that, and because I think we have time here for some dialogue and exchange, which I very much welcome, and welcome others who have different experiences and different points of view, and glad to exchange and share thoughts.
Thank you so much, Dale.
Yeah, thank.
Great presentations. Do you like me to stop sharing or keep your?
Yeah, you can stop sharing, and maybe we can then see each other, or people can raise however.
I have a question slash observation, Dale. I would have to say, spending the last 20 years of my career in research and development, we were really good at the first part, doing the research, doing the experiments. Once we got past the technology readiness level 3 or 4, though, that was where it was really tough, because we really didn't have the infrastructure in place to incorporate the thinking of process engineers and what's really needed from an operability or even an actual design point of view to incorporate this technology into our existing systems, and that was really the hardest part of what we were trying to accomplish. And I don't claim any great success, but it's sort of validating to see somebody else come to the same conclusions. That's where it gets very difficult.
I totally agree. And at that next level is, DOE then funds demonstration plants, or it can be different terminology used for these systems. But just as you say, the cost increases significantly, and there's a real need, because it's, if the concern that I have is, we have examples of where there hadn't been a lot of thought given to supporting that demonstration project, and yet that there's a real challenge here as to priorities of where we spend our time and money and effort, so that we're gaining the greatest benefit for this. But absolutely right, Chuck, or Scott, I very much agree with with that challenge, which I've experienced. We experienced that at Westinghouse in many ways as well.
Other questions or comments from those on the session? John?
Yeah, hi, Dale, that was really terrific. I appreciate how you framed that. And I like the historic examples as well, too. I mean, I think that tells us, we always kind of imagine that we're at a point in time where everything is taken care of and now this is the way it is. But in fact, it's just the opposite. I mean, the rate of change is accelerated, if anything. And so our view of the future will be wrong, because of we can look at the past to know that. I just comment on one other thing too. I mean, an important part of this work is, although of course the world does revolve around chemical engineering, we would all agree, these are all interdisciplinary efforts. And that's where I think it's kind of interesting to see how these things evolve, interacting with chemists and other scientists, as well as people maybe farther down the chain in engineering, mechanical engineers, electrical engineers. But first of all, I love being in the world where you're kind of creating new matter and creating new processes. But when I join those teams, I'm always like stunned, like, where's the flow diagram? Like, how can we even be talking about this? And almost all new concepts change entirely by when you create the first energy and material balance. Your whole perspective is like, everything, it's generally qualitatively in the right direction, but all the priorities shift around. So I think it's really interesting interacting with other people, and we can teach others to follow the flow diagram too. But anyway, again, I appreciate your words. It was very well laid out and instructive. And I agree, the challenges always are on the head. At the beginning, you have to kind of actually maintain a little bit of false optimism, because that's how you motivate things. And of course, if you're working commercially, you have to entice investors and all of that good stuff.
And I think, building on your comment, John, one of the things I find extremely valuable is doing some scenario analysis. I frequently encourage our looking at this, where we look at different future scenarios to just stimulate our thinking as to what are the options out there. And out of that, frequently, there are some common themes that emerge. One may have 5 different scenarios, but each of those 5 may have some fundamental common themes, which also are important, then can inform where you want to focus a technology development or what's going on.
Yeah, to your point, I mean, we should all be looking at the new grid mix. If you're looking at developing something that's going to be running for the next 20 years, it's going to be a different world. That's
right. Absolutely right. And just as you say, I think this interdisciplinary dimension, before, I think we've evolved from each of the engineering disciplines being pretty separate in one sense, to where there's a recognition of a need to cross these boundaries, just as you were indicating. And I think now we're seeing the need to even cross beyond the engineering boundaries. We need to really be relating to the societal, the other dimensions, and thinking about what are the implications for the community where this plant will be, or how do we optimize this system so that we're thinking about it, or what system is most effective there. So really an expanding universe for us, which is exciting in my view.
So Dale, and just jumping on that, expanding sort of the universe and the system that an engineer sort of has to consider. I'm curious, for instance, like we started off just looking at a unit operation, and now we look at the plant. We've even looked globally, and I think things are becoming more interconnected. But I think you do still need to do some of that sort of carving out a space and looking at that system before you can sort of talk about integration. And I'm just wondering if you've thought about that. For instance, I mean, we're working on a proposal for electrifying process heating.
Right.
Right now, we're sort of looking at that without looking at the interconnection with utilities, which is going to be a big challenge for utilities. Right. But you sort of have to start somewhere. And I wonder if, we have this sort of design, build, operate, how do you start fitting in sort of this integration into that? And it's a very broad question, just curious about your perspective. Yeah.
Right. I think there are, just as that example, I think there are need to look at, okay, if we're going to electrify, if you will, industry, some components of the industry, to look at what are the options for doing that, and what are the trade-offs. And then eventually one's going to have to, though, think about this as the integrated system. I find it interesting that, we just expanding on that, we think about, okay, we're going to electrify industry, we're going to have electric vehicles, we're going to have, electricity for everything. And let's do the back of the envelope calculation to see, what are the implications of that? And then after we do that, I think that informs, okay, what are the options of fitting that puzzle together? And I think right now there's not a lot of thinking going on into that larger perspective. We're looking at some of the pieces, which is important, but we also need to look at the whole.
Agreed. I love the tech, the system readiness and integration readiness levels. I took notes of that. That's great. I think we had a couple questions. Can I
say something?
Waji, yes.
Yes, this is Mirza. I have experienced 35 years of experience in the sugar refineries in processing and maintenance. I find this presentation, I am not giving any question, this is appreciation. The professor has given his theoretical and practical experience in a beautiful combination, I will say. It's excellent presentation. Thank you so much.
Thank you, appreciate it.
Thanks for those thoughts.
Waji, did you have your hand raised?
Can you hear me?
Yes.
Yep.
Yeah. Thanks a lot, Dale, for the presentation, and it's been a great insights. And I feel really lucky today to be part of this conversation. Keeping in mind, this is my early start of the career. I just started my career 2 years ago. My main question that I just wondering about that, how do you see, or how do you define the importance of involvement from other fields of engineering, like electrical, mechanical, instrument, during the initial conceptual design of a new process system or a new process?
A very good question, and important. And my experience is it very much depends on what the technology or the project is. For example, in dealing, I'll just deal with some things I'm dealing with at the moment. If we're looking at future, like we've talked a little bit about the electric grid and the future there. So clearly one has to be integrating in many of the strengths that the electrical engineer and the electrical folk bring, because the revenue, the benefits, the reliability is so coupled with this. The regulations, important to understand regulations and policy in these areas. So I think it's important that we, for any kind of technology that I've been engaged with, there's benefit by reaching out and engaging with those beyond just the chemical engineer, if you will. But who you're engaging with, my experience is, very much depends on the technology. You know, for example, we did with Westinghouse, we did a lot of work on nuclear waste processing and trying to stabilize and do that, like at Hanford, the waste plants. So the collection of skills and capability that we needed there to bring together were different than if I'm looking at you know, a electric interface with the grid and that sort of thing. But I think thinking beyond ourselves is extremely important and valuable. A very good message, because I think each of us have probably seen this. I certainly see it, that frequently we have researchers, for example, who are really just totally focused on their particular piece, and they have tremendous understanding and capability there, but there's a need to engage beyond that. And one of the ways that I think we can, and I think as chemical engineers, we can provide that bridge and that opportunity for collaboration.
Great. So we're getting close to the end. Maybe one more question. Let me share my screen.
No, I very much thank you for the opportunity and really welcomed our exchange here. And if there happen to be further follow-up questions or anything, I'm pleased to follow up and engage with anyone. So thanks, Michelle. And
Thank you, Dale.
Thanks, Scott.
Thanks a lot, Dale. Thanks a lot. Thank you.
Maybe,
Thank
yeah,
you,
great
Dale.
presentation.
Thanks, Dale. It was a great presentation.
Please
Thank you very much.
join our community. It's AIChE.org. Communities. Anyway, you can go on AIChE website, pull down the menu for communities, and you'll see Community of Process Engineers, and you can access it that way. Or email me at michelleb@aiche.org for more information. If you have any suggestions, recommendations for speakers, please let me know. And Scott, are you still on?
Yes.
Okay, I didn't see you and didn't hear you, so I don't know if you want to say anything before we close.
No, just again, thank you everybody for participating today, and Dale, another thank you for an excellent presentation, thought-provoking, had some good questions, generated some good discussion. So thank you very much from the Community of Process Engineers, and we will look forward to seeing you next month.
Great, thank you, Dale. Thank you, everyone.
Thanks, Dale. Bye, everyone.
Thank you.